So the last time we started to talk about online learning, how it's different than batch learning and planning and all that. Defined regret, which is shown here, which is also called, cumulative regret, and that we can study these problems in undiscounted problems. Mostly that's what we do, and infinite horizon, fixed horizon. And we said that, okay, we're gonna start with the fixed horizon setting because that's the easiest. And just to recap the notation, we said that there are going to be episodes of length h. Within an episode, the stages are numbered by lowercase h. The index goes from 0 to h-1. And there will be k episodes. And within an episode, we're going to have a sequence of state action pairs. The first state that we encounter comes from this initial state distribution mu. And then we go in, select some action that results in the next state, select another action, and so on and so forth, up to the end, where we also going to get the very last action so that we can learn about the transitions all the way through the episode. So this is for a fixed episode k. So that's the uppercase index there. And so here the assumption is that there is this MDP that's described by these four tuples: states, actions, transitions, and rewards. And the next state is always distributed according to the transition probabilities defining the MDP. And for simplicity, we assume that the reward is known. And then we define the regret as the difference between the value we could have gotten if we act optimally from a given initial state for a given episode. So that's V0 star at the initial state of the case episode. And we compare this for every k to the total reward that is received within that episode. Okay. And then we said that we're going to be happy if the regret per episode goes to 0. So if the regret per episode goes to 0, as k goes to infinity, either in expectation, so that would be a minus goal, or with high probability, or whatever, almost surely. People don't really talk about that. And just focusing on the regret still, if you have this episodic problem and the episode length is 1, then you get what's called contextual bandits. And if the number of states is also 1, then you get what's called finite unbandits. In this case, the reward would be assumed to be unknown, because otherwise there's not much to learn, and you will have 0 regret, or every reasonable algorithm would have 0 regret. And already for this bandit setting, you can study epsilon greedy, other simple mechanisms. They get suboptimal rate of growth of the regret as the number of interactions goes. So here n, in general, n is the number of interactions in an episodic problem, n would be k times h, where k is the number of episodes. Like at the end of the case episode, the total number of interactions you had with the MDP is k times h. Whereas better algorithms can achieve square root n growth of the regret, and so the average regret in all of these cases goes to 0. And so what are these better algorithms? So one idea is to use what's called optimism in the face of uncertainty. And we talked about that This is a general idea that applies quite generally, but it's not completely universal. So there are some cases where it wouldn't work very well. But surprisingly enough, it's a reasonable algorithm in general. So this idea goes back to Lauren Robbins and Pierre Kumar. And so now we are after our first specific, okay, so what was the idea of optimism in the face of uncertainty? The idea was to, given the information you have, you discard all those possible words, all those words which don't look very plausible to you, and amongst the remaining words, choose the one in which you can get the best rewards, and then follow the policy corresponding to that word. So that's the optimism principle or schema. And so if you want to instantiate this in the finite horizon MDP setting, how does it look like? Well, we'll need to come up with some way of constructing the set of possible words. What are the words? Well, we said that we're going to assume that the reward function is known and the transitions are unknown. So the set of possible words are going to be just a set of transition probabilities, transition dynamics, those that are close to the empirical estimate of the transition probabilities. So those are the likely one. And so we're going to choose here this beta later. We said that we're going to choose it later in such a way that with high probability, this set for every episode is going to contain the unknown transition probabilities. So P star is in CK for every K with probability 1 minus delta. So the beta is going to be chosen as a function of delta, but otherwise beta is going to be just depend on, so the argument of beta is going to be the number of times a given state action pair is visited, which is also used in constructing the estimates of transition probabilities, right? So because the estimates of the transition probabilities are going to be simply the count of how many times we have seen a transition happening from a state given an action to a next state, divided by how many times we have seen data where the given state action pair was even visited. And if that count is 0, then we just assign 0 to all the transition probabilities. And then we said that, okay, let's choose beta 0 to be 1, because that makes sure that the CK is the full set of all possible transition dynamics, so that sufficient to guarantee that initially, at least when we haven't seen any data, P star is not lost. And then we have to take care of the rest later. Okay, and so in the choice of, in the design of choosing beta, the goal is to have both that we are not losing the true model, and also that CK shouldn't be too large. We'll see how to get such confidence sets. There are many ways of designing these. Some are better, some are not that great, but pretty much all of them are quite decent. And so now that we have C of K, so this is basically the set of plausible models. We can choose for the policy which is optimal amongst all those. It's optimal policy of the MDP whose transition probability gives you the maximum optimal reward amongst the plausible ones. So P tilde of K is going to be the optimistic model. And then you just choose the optimal policy in the optimistic model, and you follow that policy up to the end of the episode. And what's missing is we don't yet have the construction of the confidence set because beta is not defined. And the other portion that's missing is the understanding of the regret. Like, how do we analyze the regret? So that's where we're going to continue today. Okay, so I think Vlad was asking the question, how do we do all of these calculations? The last time I mentioned briefly that this calculation may not be trivial to do, and a lot of times it's quite challenging, and then sometimes you even stumble upon computationally difficult cases. The way you can help yourself is that you can relax a little bit the definition of the uncertainty set. So for example, in this case, if I want a computationally efficient implementation, I can get that at the price of slightly increasing the regret, slightly or not, like it's increasing by a factor that's proportional to the number of stages, age, by choosing a different transition model for every stage, and then do a backwards calculation, starting from the last stage and then calculating everything backwards. So not sharing the transition models across the stages makes this calculation possible to do. If we started with a model where the transition, like the states that you can encounter in different stages are all different, then we wouldn't be losing anything. In general, with this, you can lose something. And then I don't know whether we have an efficient implementation for the shared case, for the shared general case. I guess some other algorithm, yeah, Alexis, for AQR, yeah, like there are other cases where you have like completely efficient implementation. Even for this case, for a different algorithm, which does, like you can view that algorithm as an optimistic algorithm, which would run an optimistic version of value iteration, and you can prove that, well, on one hand, that's computationally efficient. On the other hand, it is still going to get the same guarantee. So I'm telling you the story from the perspective of kind of like running a model-based algorithm, where you could have different models of the world, and you're choosing between different models, and then a model dictates what policy to use. And but for the calculation, if we looked at this relaxation, you would see that I would be just running value iteration backwards with some extra bonuses that come from these transition probabilities being chosen in an optimistic fashion. So in every round, choose the transitions in an optimistic fashion, and you just run backwards value iteration. Then that can give you the idea that, okay, maybe this value iteration thing can work more generally, and indeed it does work, and it gives you the optimal bounds, and I will give you the references at the end to where this is all written up. But it's a good question. It's a lot of times a delicate issue that one needs to carefully look at, because it's not for free that you could just compute these things. And oftentimes you deviate from the like the simplest approach, which is what I'm presenting today, for the sake of gaining computational efficiency. And then you have to carefully redo the proof and show that even with that approach, you can get the same bounds, or in that case, maybe even better bounds, because those guys are going for like the variance effect. We talked a little bit about the variance effect before when we were discussing that if you are estimating models, then you can get better bounds if you are more careful with treating the variances, this Bernstein type of bounds. And you can use that in online learning as well to get a better dependence on generally the horizon, but like these constant factors can be improved. Usually the horizon dependence can be improved by doing a more careful analysis that takes into account the variance. Anyways, excellent question. So how do we choose CFK? So for choosing CFK, we want these two things. We should never lose P star, and CFK shouldn't be too large. And it may be worthwhile to think a little bit about like, so when we are estimating these transition probabilities, all that matters in a way is how many times you have encountered a given state action pair, right? And for different state action pairs, you may have different counts. Like some state action pair is visited a lot, some others are not visited too often. And for the ones which are visited a lot, we expect that we should have a much better estimate for the transition probabilities. And because of the Markov property, actually, we should have a much better estimate. It's the Markov property basically allows you to decouple the past from the future. And here the future just represents like, oh, I just visited the state action pair. What's the next state? And the state action pair, just the fact that you have the Markov property, and you know that you just visited the state action pair, that means that you can forget about what happened in the past. So in a way, the Markov property immediately tells you that, well, this estimation thing kind of just behaves like as if the data was IID, right? So if you visited a state action pair U times, U is just an integer, okay? So fix an SA pair. And so let's assume that U was visited, SA was visited U times. And let's denote the estimated transitions by P of U of A. And so for every visit, we got this, next state, and we were just counting how many times we have seen one particular next state versus another particular next state, right? So then you can think about that this is nothing but, let's say, this is nothing but a bunch of, what letter to use? A bunch of visits. The number of visits goes from 1 to U. And every time when you were here, let's say the data was like, let's represent the data on the V's visit by XV. So this is going to be a next state, right? So this is the next state that you encounter when you visit state action pair SA, the V's time. And then the estimate is just going to be simply counting how many times we have seen a particular next state appearing in our data. And the Markov property is going to imply that this data, xv, where v goes from 1 to, I don't know, u, is IID. And it follows the distribution of PA of S, right? So the probability of seeing one of these next states is exactly, okay, I think that there is a star because I said that I'm going to use stars for the true transition probabilities. So the Markov property implies this. And because this happens to be true, so recall that what we want is that we want to show that P star is within the confidence set. So that just means that if I replace this P by P star, okay, I want to show that the one norm deviation between P star and whatever transition probabilities I have is going to be smaller than beta applied to the number of times this thing was visited, which is U now, right? So what we need to calculate is the one norm of the deviation of PU of A S and PA star at S, right? So we want to say that with high probability, with probability 1 minus delta, this is small. And the one norm, so here it's useful to remember that the one norm has a number of properties, and one of the properties is going to be that it can be written as the one norm of any vector, the one norm of vector P, or I don't know, okay, vector P, let's say, can be written as the supremum of the inner product between the vector P and the vector X, where X is in the hypercube of radius 1, this L infinity or maximum hypercube. And if you think about it, the supremum, it says like any vector, take any vector which is in the hypercube and take the inner product with this vector P and take the supremum over those. Well, the supremum is going to be taken because this is a linear expression. So it's convex. And the hypercube is convex. Then this function is going to be maximized. The convex function is maximized on the boundary. And in this case, it's going to be on the vertices. So I can immediately write that this is the same thing. This one norm is the same thing as the maximum over all possible S-dimensional vectors that take values in plus minus 1. So those are the corners of the hypercube. Those are the only vertices of the hypercube of the inner product of the difference between the estimated transition vector and the true transition vector. And so now, if we want to upper bound this one norm difference, then we can just focus on, for a given X, let's just focus on this difference with this inner product. And then eventually we're going to apply a union bound. So now fix some X. And let's take a look at this difference. And I just plug in the definition of PU of A. So Vlad was asking why use the one norm instead of something like the KL or whatever other differences. It's because in our analysis, we'll find it very convenient at a later step to use the one norm. So it's just a good fit for the way the analysis can go on. But it's like, yeah, at this point, it shouldn't be very clear of whether one should use the one norm or not. You're right. But later on, well, we can come back to this when we do the analysis that, oh, yeah, like this is where we are using it, and whether we could use a different norm, whether we could gain something by using a different norm. It happens that not really. What you could gain with is, we'll see, if we brought in somehow the variance, but we're not doing that. It's a little bit beyond what can be presented today. Okay, so just plug in the definition. So P of U was the sum, and there was a 1 over U. So I'm going to bring that out. And then there is the okay. And then there is the other sum, which is over the states. And so then there is this indicator that x of, okay, we call this, oh, look at that, lots of different letters. This should be a v. We were using a v before as the running index, and this should be s. Well, s prime, right? Because s is already taken. And this should be compared to P star S and S prime. Okay. S prime is taken? S prime is not taken. S is taken.
So is it XS prime or just XS?
Hmm?
So this is XS, not XS prime?
Oh, this is XS prime. Yeah, that's right. They're just expanding the inner product, and then I have to name somehow the index, and the logical name is like S prime because it logically represents the next state.
Okay.
Okay. So here we have an average of U terms, and we have all these terms. So let's call this delta of V. So you can just write this as 1 over U sum of V goes from 1 to U of delta of V. All right, and so what do we know about the delta? We know that they have 0 mean. We also know that the delta is well, if you sum them separately, then you will see that like this indicator can only be 1 at once. So the first term of the sum is either +1 or -1, and the other term of the sum is the average of values between plus and -1. So you're taking the difference of a value which is either +1 or -1, and another value which is in between plus and -1. All right, it's the other way around. We have some conventions, higher values to the right. And so here is this other value, and so the largest difference here clearly is at most 2, right? So all of these are at most 2. And we also know that the delta V is an IID sequence, as we discussed, because of the Markov property. That would call for some proof, but you just use the Markov property and the definition of what it means to be IID, and you can just apply that to XV. It's a little calculation, but it just verifies. Later on, I will talk about another way which avoids the verification of that this is IID. It turns out that we need to do something slightly more general than what this is it, but this is still kind of neat because you can reduce, because of the Markov property, you can reduce things to the IID case. I think that that's important to remember. And so now we have all of these are satisfied, so that we can use Hovding's inequality, right? So Hovding's inequality immediately tells us that for every delta with probability 1 minus delta, 1 over u times the sum of these deltas is at most, well, there is the maximum or the range parameter that comes here. So that's 2. And there is log 1 over delta divided by 2 times the number of terms, 2 times u. Okay, so that's what Hovding's inequality buys for us for a given fixed x. But now we have a bunch of x's, right? So how many x vectors do we have? We have, so what's the constraint on the x vectors? They are the corners of the hypercube. The number of these corners is 2 to the s, right? So we have to split data in 2 to the s ways to get a bound that holds with probability 1 minus that, and that holds for every x simultaneously. So redefining data to be data over 2 to the s, basically union bound, implies that still with probability 1 minus delta, simultaneously for every x, this difference is of the same size. But this simultaneously for every x is of the same size. So therefore, if the maximum is of the same size, that means that the one norm is of the same size. Well, the same size with data replaced by data over 2 to the s. And so if I plug in the the data over 2 to the s, then there will be two terms with the log. In one, you have s times log 2, and then in the other, we still just have the log 1 over data. Right? So now going back to, but we don't want to bound this. We want to bound, we want to say that, we want to choose this beta such that for every S and A, so what is this? So here we had for every S and A and for every K, P star is included in all these inequalities hot, right? So we need to use a union bound over the states and actions, and we also need to vary about like the range of K, or like when you are at a given point, this nk is a random index, right? But this PA of K is definitely going to be one of these PUA of S, right? So if I list, so there is the PK of A and S, which is what we want to say that these are smaller than with some beta of this NK of SA for every K. We want to show this, that this holds, and for every S and A. But we have arguments for this PU, but for a given SA pair, this PAS of K is equal to P of N of K of SA of A of S, right? Like with this other notation where U is the number of visits to that state action pair. So take the first time when that thing was visited, you construct the transition probabilities, and now you have to prove something for that. So in other words, if we take a union bound for all possible values of U, we should be fine. Then we are covering for all possible values of NK of S. So take union bound over U and S and A. So how do we take union bound over U? Like how many U's can we have? So usually we just split data equally amongst those. So we could start to argue that, oh, if the total number of, I don't know, visits is going to be at most capital K, then every episode has 8 steps in it, then the maximum number of visits that any state action pair can get is capital K times H. And then you take a union bound over that. That's possible. Then your algorithm starts to depend on knowing the horizon, knowing this capital K, which is like, yeah, maybe you want to have an algorithm that doesn't need that knowledge, that you can just run without deciding ahead of time about for how long you want to run this algorithm, and you can you still want to maintain the guarantees. And there is a cheap way of doing that. It's losing a very small constant factor, and it's not the like you could do that with something like the doubling trick, if you have heard about that, but it is much easier to do that. So you need to take a union bound over a countable number of things, then you can do that because we have things like 1 over, I don't know, U times U plus 1. So basically, 1 over U squared sums to a finite number. And then if you're a little bit more careful with these sums, then you can notice that this just sums to 1. So 1 over u times u plus 1 sums to 1. How do we know that? I guess that's true. Yeah, when u equals 1, you get 1 over 1. It's telescoping, right? Yeah, Queensland. Good. You wrote it. Yes. So it's a telescoping sum. It's absolutely summable. So you can just like take the partial sums and like you see that the partial sum is 1 minus 1 over the very last terms plus 1. So that goes to 0. So the whole thing is summable and converges to 1. So it's a very useful, neat trick. How do we use this? Well, you can multiply this equation by data, and so that's how you split your data into infinitely many parts. So when the number of visits to a state action pair is u, you say that, well, I don't want my confidence interval to fail with more than delta over u times u plus 1 probability. And the total failure probability is still going to be delta. But we also need to divide not only by u times u plus 1, but also by the number of states and actions. So this is what results into the final expression. So putting everything together, you have this 1 over delta here. If you replace the delta there with delta over u times u plus 1 SA, then you get a union bounded, like that you get that all these inequalities hold uniformly over any number of visits to any of the state action pairs. Therefore, we're going to be done if we also show how to choose the beta. But the choice of the beta is going to follow from what choice. So it follows that with probability 1 minus delta, for every u greater than 1, for every SA state action pair, the one norm difference between PUAS and PAS star S is at most 2 times S log 2. And here I have to write as log u times u plus 1 SA over delta and divide by 2u. Okay. That's not really easy to read, but hopefully the idea is clear. You just, yeah, we splitted the data. So that means that we can choose beta of u to be just this expression. Right? And if we do this, then we get our first lemma. With beta as above for every k. Sorry. For every delta, or it holds with probability 1 minus 1 that P star is in the intersection of all these confidence sets, C of k. All right, so there we go. We have our confidence set. We have our beta. So next step is to do the regret analysis. So let's do the regret analysis. We're going to prove a high probability bound on the regret. And an expected regret bound is not that hard to construct from this. So let's fix a delta and choose beta as above. And consider the event when P star is in the intersection of these confidence sets, right? So when we are not losing this. So by lemma 1, by lemma, the lemma, the only lemma that we have so far, lemma 1, this has a high probability. That's good. So it's going to be sufficient to argue that, like, on this event, nice things are going to happen to the regret. If we prove that on this event the regret is small, then we know that with high probability the regret is small. So that's how we're going to do it. So in what follows, just assume that we are on this event. That is, P star is in the intersection of the confidence sets. All right. So what's the regret? So the regret was we have these k episodes. In every episode, we have an initial state, and then we have all these values that we collect, right? So Vk is the sum of rewards that we collect within an episode. And the regret is just the difference between these two guys. So let's fix a given k. We're going to argue for every k that this is not too large, and then we sum up or whatnot. And recall how we constructed our policy. The policy was optimistically chosen. First, we chose this model, P tilde of k, which was this optimistic model. And we use this notation that, okay, if we have a value function for a policy or the optimal value function, we start to index the value functions based on transition probabilities, which are the things that differ between the models. Okay, so we choose P tilde of k, and then we choose the optimal policy there. So that's what we know about the choice of the policy that we have. So this gives us the idea that maybe we should write this as, so you have your nominal model, P star, oops, and the optimal value there in that model. This extra index 0 is going to be needed because, well, earlier I was just suppressing it, but it should have been there. It denotes that, like, okay, we are at stage 0 in this problem. Here we see that, we'll see that we're gonna need this. Right, so let's compare this to the value that the optimal value for this model that is optimistically chosen and at the same initial state. And then, okay, we subtracted that, so we have to add that back. And okay, so this value is exactly the value of the policy that we choose in the case episode. So whether I put a star in the upper index or I put pi of k in the upper index, it shouldn't matter, because pi of k by definition is the optimal policy for the MDP whose transition probabilities are given by p tilde of k. And of course, we are not in p tilde of k, but we are in p star. And we are executing this policy from this initial state. So we subtract this value. Now we're going to compare this to v of k. All right, so we have three terms. Term number 1, term number 2, and term number 3. So we will show that all of these are nicely behaving. So for term number 1, that's really simple. It's upper bounded by 0. So that's a very quick argument. Why is that? That's because P star is in CK, because we are uneven E. And we solve the maximization problem of the optimal value of the initial state over CK. And we found that P tilde of K gives you the maximum value. So it definitely gives a value at least as large as P star, which is also in CK. So here we were using that CK is carefully chosen, and we were also using optimism. So this allows us to not worry about too much about like where the optimal policy would go. So in a way, like the difficulty in the regret analysis could be that like the optimal policy may choose to go some way and our policy is going some other way. Like, how do we reason about that? Well, we don't, because we just choose optimistically. So we just cancel the effect of the optimal policy in this way. We say that, well, okay, like there will be some price for this, but we will show that the price is not too high. Okay, so first term is easy. The third term. Okay, so what is that? So on one hand, we have the actual value of this policy pi of k. On the other hand, we have the sum of rewards up to the end in a trajectory that is generated by following policy pi k. So the expected value of this, if I take the expected value of this, condition on the past, whatnot, condition on S naught k, then I get exactly the value, right? So this is like noise in a way, right? Like it's a noise variable. It has a zero mean. Between different episodes, like for every k, I'm going to have a term like this. So let's call it psi of k, all right? So we have these terms, And for every k, it has a mean of 0. And the psi of k is between, I don't know, well, all of these values are between 0 and 1. So the first value is between 0 and h, and the second value is between 0 and h. The difference is between 0 and h, right? So, so the range of psi of k is at most h. So, yeah, or I could say that psi of k is in 0 and h, right? To be more specific. Is it 0? Could be, no, it could be, okay, so it could be negative h to h. The range is okay. Whether I lose a factor of 2 or not, it shouldn't matter. So between minus h and h. But you can like remove that factor of 2 if you're a little bit more careful with the analysis. And now, okay, it must be tempting that to say that, well, we're going to have the sum of these values. And we want to argue that this is small. That this goes from 1 to k. They're not independent. So what jumps to mind is that we should use Hovding, but they're not independent. Because the policy that we choose in episode k depends on all the data that came before. Definitely they are dependent. Okay, so we have noise, but somehow it's noise in the sense that the mean, even when you're conditioning on the past. So here I can condition on all the past information, all the data that came in previous episodes. I get 0 mean, right? But they're not independent. So when things like this hold, then you say that you have Martingale differences. So if you have a sequence of random variables, and it holds that condition on the past, they do have 0 mean. So that's called Martingale differences. Martingale differences, by and large, behave the same as IID. So Hovding's inequality would have told us that this sum would be less than equal to square root k log 1 over delta divided by 2 and multiplied by the range. And it turns out that the same holds even for Martingale differences as well. So this is a Martingale difference sequence. And by and large, you should think about that they are like the advanced 2.0 version of IID. Basically, what you can do is that you have like a random walk, and all of this can be seen as the analysis of random walks. So when you have these 0 mean things that just like a random walk, and in the random walk, you're evolved to some point, you look at back the history and you choose a new distribution. And in the new distribution, the distribution itself can depend on the history, and it can have like weird properties, but it should be 0 mean. If you do that, you can try to choose it in a strategic manner if we not allow the tail to become really large, really wide. If you add this next increment, then it behaves as if there was no strategic choice in the distribution. And that therefore, these are called Martingale differences. Martingale is this ancient term for some gamblers used it, And this whole analysis comes from trying to understand whether you can win in sort of a fair game. And like the conclusion is just like if you're playing with this probabilities, like they can go up and down, but like the unbiasedness is kept, then nothing really changes in these games, right? So the expected winnings are going to be 0 all the way, and the tail behavior is kind of repeats what you see in the IID case. So you can't make it worse than the IID. IID is kind of the worst for these. And so this inequality that extends Hovding's inequality is called sometimes just Azuma's inequality, sometimes it's called Hovding-Azuma. And it is one of those inequalities that is, have been many times discovered by many different people. And it is not named after the first discoverers as usual, but like it's okay because those people got some other inequalities named after them, which they didn't discover probably. So it's all goes around and comes around. It's fine. Anyways, so we have that this term is under control. Okay, so this will call for a union bound, right? Like, so here we want to separately argue for this psi k terms, and then we want to say that like, oh, it's probability 1 minus that. This is also small. And so now, okay, we have to think about like, okay, like the error event is going to be like any of the two error events, that either the psi k is not that small, or the p star was not in the intersection of these confidence sets. Okay, like, okay, it's a 2 data error probability. And if you don't like to say at the end that with probability 1 minus 2 data, your final regret bound holds, then you should just like split the data in some way between the two cases. Maybe you change the probability, the confidence parameter used in the confidence set construction. But okay, I'm just going to say that, okay, let's just remember this is going to be a union bound. So here we collected another error probability of data. So the final bound is going to hold for no with probability 1 minus 2 data. All right, so there's the third term. And okay, going back to the argument with the IID and the Markov property, you can just directly use this Martingale difference argument there as well. You don't have to go through the pain of proving these independence properties, although it's fun to try to do that. And it has some other benefits if you try to do that. Okay, so let's return to the remaining term, which is term 2. So we have this p tilde of k and p star, and we were careful so that we have the same policy. So here you see pi of k in both cases. So the only difference is that this is for different MDPs. And then when that happens, then what is the first thing that comes to mind? Well, we have already seen this, right? How to deal with this. When we were talking about batch learning, at the very beginning, we were estimating models, and then if the models do not differ too much, then the values are not going to differ too much. It's like a value difference identity that you need to use, which starts from using, the recursive form for the values, or the Bellman, I don't know, Bellman equation for the values of these policies. And we were doing that in the case of the discounted case, and this is the finite horizon, so that's a small variation, but it's by and large the same. Like, we expect these values to be close to each other if p tilde and p star are close to each other. And we just need to show that that holds. It's the sensitivity of the values with respect to the transition probabilities. And we have seen that in the past that, okay, these things are not too sensitive. That is a blow up of the error by a factor of, I don't know, the horizon or something like that. We should totally expect to see that. but by and large, that's all. So okay, so let's see how how this is done. There are some delicate issues here. Right. So just copying. All right. So as I said, so here in cases like this, it's good to remember. It's basically you want to use the Bowman equation in a way to study this sensitivity question. And so for here, just remember that V of HP of pi at some state S. Well, okay, so let's get rid of the states, just write it as vectors. It's going to be the reward for the policy. The rewards are not dependent on the stage or transition probabilities. And then M pi, which is like creates the reward, the policy dependent transition probabilities from the policy independent transition probabilities. And then you have V of H plus 1 of P of pi. So that's kind of the recursive relationship. And so that holds when H goes from 0 to H minus 1. If we define V of capital H of P of pi to be 0. Okay. And so just plug this in, and then we have the pi star and the P tilde K, and let's see what happens. Oh, it's a lot of writing. Yes. I guess I don't want to write as much. Later on, I'm going to write more, but it's just too much work. So how about like we just write this, and let's be a little bit more generous. So go for stage H, some policy pi, and then there is P star and there is pi, P, and so the rewards cancel, and there is M of pi, and then there is P, P star, and okay, so I want to switch to, which one do I want? I want to bring in this difference as soon as possible between the transition matrices. And then, okay, because I write this, I need to add a correction, right? So I introduce this term, which was not there in the difference, because in the difference I should have, here I should have a P in the second term. So I have to correct for that. So I have to add this back. And then okay, this is, I have to add it back. And then I have to subtract it, right? So this is correct. This is fine. And you can see kind of a recursion evolving here, right? So the difference between the values at some stage is recursively written as a difference of the values of the next stage, and some correction term that comes from the differences of transitions, which are correlated with some value function for the next state. Now this is all fine, and you could have the instinct that, okay, let's just take the sup norms and then sum everything up, and these differences between P star and P are going to come out, right? And if this sup norm differences are going to be small, then we'll be fine. The problem with this is that the sup norm differences may not be small. The problem is that we don't actually want these sup norm differences to be small, because we don't want to visit those state action pairs where the optimal policy wouldn't go to. We have the least intention of doing that. So taking the supremum norm here would be a bit reckless. You don't want to do that. We need some more refined argument. So what can we do? Well, looking at this, we might notice that, well, there is some recursion going on, but it's not ideally written for my case. And the recursion is that, okay, like errors at some stage are related to the errors at the next stage, but there is some random transition going on according to the policy. And then that might give you the idea that, well, hey, maybe we can use this to our advantage. The problem with taking the supreme norms is that, well, we need to stay closer to the data that was experienced. So so somehow, yeah, like it seems that we are saving a little bit on writing things, but not writing that, okay, we only need the differences to be small at where the policies went to, but this is going to lose something. So now we want to put back those states and then think carefully about where the policies are going. And then when we see this this recursive expression, if we only had P star here, then we could just say that, well, okay, if this was P star, this is just an expected value at the next state of the difference between the values. And okay, so since this is the expected value, we can replace it with the actual difference at the next state, which is sampled from that distribution. And the difference between the two is going to be like noise. It's again a Martingale difference sequence. So you cannot not worry too much about that. And this way we can stay closer to the data. We can avoid taking those supremum norms. So indeed, this is what we need to do. The last problem is that I ended up writing this recursion in an unlucky way. I have to flip the P and the P star, because I want to see P star here because that's where my data is coming from. But that's not too hard to do, right? So I can just like equally valid is to, so now that I understand what I need to do, I can start with writing, oh, I want P star here. Okay. So if I want P star here, what goes here? So it's VH plus 1 P star of pi. And I need the value differences. Okay. And now I have to correct for what I don't have and what I wanted to have, and that's p star minus p times vh plus 1 p of pi, right? So let's use this symmetric form. And when we do this, then now we have to be a little bit more specific. So we are in episode K, and on this stage H, in this episode, and we take this value difference, right? So this is the fully decorated version of it. So this is, okay, let's call it delta H of K, right? So we wanted to bound delta 0 of K. That's clear. So we define all these deltas because we're gonna have a recursion and some fun with this recursion based on basically this identity. So recall that, so this is just delta 0 of K. Okay. And so the identity tells us that delta H, so it's basically plugging in this identity pi k, here plug in p tilde of k, use this at this value as s of h of k on every point, like just plug in this value. So that goes here, that goes there, and then read out what gets out. And here, so what I said was this expected value thing, and just use that. So that's what we're gonna do. So delta h of k is equal to all these pi's are pi k. This is pi tilde k. Oh my gosh. Pi tilde of k. And VH plus pi tilde of k. All right. So the first term, so that's the expected value when I start at state shk, make a step with my policy pi k, and look at the value differences at the next state. So that's delta h plus 1, okay, right? And this was just the expected value of that. So now that, so this was the expected value of delta h plus 1 k, given like all the data that happened before this stage, including the state And so, all right, so this is going to be, well, I don't want to copy that whole thing, so I just write this expected value. So here the conditioning is on everything that happened before this stage on this episode, including SHK. Right? But we can just denote this by a new letter, H, 8 of H plus 1K. This is noise. This has zero mean by definition. It's constructed in such a way. So the other term is the difference between expected values, but it's worthwhile to write that out because that's the term that we will need to really bound. Okay, so here is what I'm going to use. I'm going to use the difference between, let me write it this way. MP and P, oh, this should be star in this other corner. So if you have something like this, evaluated at S, then, well, okay, so this policy pi actually chooses at state as action A, let's say, okay? So then first of all, you can write this whole thing. It looks complicated, but it is just P of A S minus star, P of A S, and inner product with V. That's it, right? Just this. And it's upper bounded by the one norm difference between these two guys and the supreme norm and the max norm of V. Okay. It just, that's called Herder's inequality. If you have conjugate norms, like the one norm and the max norm, then the inner product between two vectors is upper bounded by, you know, like taking the norms of the conjugates. So the second term based on this can be upper bounded. So here the policy takes the specific action, which we called A of H, okay? And you're at this stage H in this state, and then we have this other transition probability. Take the one norm, and the max norm of the value functions at any stage can be bounded by H. So I'm just lazily going to put an H there. Right, so here, the second step, what the inequality was using this little inlet calculation. And so we see that this whole thing is upper bounded by data H plus 1K plus 8 H plus 1K plus, and here this is upper bounded by this beta, right? Because we are on this event E where P star is in a confidence set. So I guess, okay, this is 2 beta because like both of them are at a distance of beta from the empirical estimates. So 2 beta, and then I have to put in the number of visits at, I don't know, so this was the number of visits at the beginning of the episode. So let's not forget that this is that. And for this specific state action pair that we are using in this recursion. Now you can unfold the recursion. You will have a bunch of noise terms, and then the end, this data age of k, it's just going to be a big 0 because all these value functions at the end are 0, so that difference is just 0. So eventually the delta, where is the delta? The delta age is defined as value function differences for little h equals capital H. It's just 0 by definition. So this is 0. And so that's where the recursion stops. And now we're left with that delta 0 of k is smaller than equal to eta 1 k plus eta h minus 1 k, I guess eta h. Yeah, I guess that would be 0. So it's enough to go to eta h minus 1. And within the trajectory, we have to go from 0 to h minus 1 with all these betas. And now we will need to argue about that. Okay, this is going to be noise. Should be fine. Martingale differences. We have to argue that this is never going to get too large. But I'm going to do that next time. Right? Any questions?
Shaba, I suspect there might be a small typo in your regret decomposition when you decompose the regret into the 3 terms.
The 3 terms, okay.
Yeah. Yeah, I'm not sure if all of this. So like in the number 1, like the first term comes from the original equation, and the second term, and you expect that second term to cancel with the first term of number 2, but one of them has pi k.
The pi k here?
Yeah, but one is a v0 star and the pi k. Yeah, is that like?
Yeah, pi k is the optimal policy for p tilde k, this model.
Oh yeah, okay. But it's not the optimistic policy, right? Oh no, okay, never mind.
It's the optimal policy for.
Yeah, okay, right. It's the optimal policy for the optimistic model. Okay, got it. Yeah.
Yes.
Yeah. Okay. Yeah.
Good point. Yeah.
Thanks.
All right. Let's stop. Then